All right, so we lost juice before. This is basically, let's see, where are we here? So we get rid of an unknown here, substitute, and then to solve that, you work over here, you isolate it, and then basically set it up to solve. And fun will be had by all. I want to point out that the equations that I typically give you are the ones that are at the end of the chapters. In the momentum section, it's chapter 11. These equations right here, under special cases, I'm not giving them to you. So I will not give you these equations. Because it takes away from thinking about the problem of setting it up properly. And students who rely on it in the past, when I put them on there, most people who use them improperly because they are more specialized. So, don't think it helps. I do want to look at the two-dimensional collision in a very special case. If the masses are the same, and one of them is at rest, I know that 4 kilogram mass will shoot off at some angle theta, and this will shoot off, we'll call that theta 1, and you know, instead of theta and theta, I'll use theta at phi. And also because I just started a new file here. If I botch this, I will delete it and no one will ever, besides you three, we four, will know about it. Actually, let's just make it more generic than that. Some mass m, some initial speed a, with C and D. So A, B, C, and D, the same notation I've been using. All right, so what's my total momentum?
MA.
Yeah. So P initial is equal to M A. I guess I hat. I know the direction of momentum is the same direction as velocity. Those are the only two vectors in the momentum equation. So, therefore, they have to be in the same direction. So, I'm going to let that represent MA. Now, after the collision, I know that this one is going to be shooting off at some angle theta. And this one's going to be shooting off at some angle phi. And the sum of those momentums has to be my initial momentum, since momentum is conserved. So this would be a magnitude of MC and a magnitude of MD. If I look at my, again, perfectly inelastic leftover stuff here, not one dimensional anymore. Perfectly elastic kinetic energy is conserved. So what would my kinetic energy equation be?
K equals M cosine of theta.
Oh, you're going way complicated if you're doing that.
Oh.
So first off, what's my initial kinetic energy?
No, it's just MA.
1/2 MA squared.
That's it.
Oh.
So that's my initial kinetic energy. My final kinetic energy needs to be the same since it's perfectly elastic. What would my final be in terms of C and D?
1/2 MC cosine
You're still going way complicated.
C squared.
Squared.
um,
Not worried about direction with
Right.
energy. Plus.
1/2 D squared.
All right, so I have this nice little equation. What can I get rid of? If I look at that relationship.
1/2 in the mass.
All right, so if I divide by 1/2 mass or multiply by, I guess, 2 over the mass, I end up with A squared is equal to C squared plus D squared. If I multiply by the mass, say I kept the mass in there, depends on how you want to look at it. If MA squared, the M is not squared, if MA squared equals MC squared plus MD squared, what does that tell you about this triangle?
Right triangle.
It is. That's the hypotenuse right there. That is a right angle. So, if we manipulated that a little bit, that angle there would be what I would call phi prime. That is theta prime. I know that theta prime plus phi prime is 90 degrees. This is just 90 degrees minus theta plus 90 degrees minus phi is equal to 90 degrees. We end up with, well, dot, 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 theta plus phi is 90 degrees. So in this one special case of one mass is at rest and both masses are the same value, that would be a right angle there. Just another way of looking at it.
So these are two masses that are have the same mass,
Yep.
and the right one is at rest.
Yes. So, if I gave the following rule, I have a 3 kilogram mass heading to the right at 6 meters per second, and a 3 kilogram mass heading to the left at 2 meters per second. How can I get it into a problem like that?
How exactly do you mean?
Well, this one over here has the condition, masses need to be the same, check. That one of the masses is at rest. So how can we put one of those masses at rest.
From the perspective of the right one,
Say it again?
to evaluate the problem from the perspective of the right one.
Okay, yep. And so what does that mean in terms of, what would,
So that one would have 8 meters per second.
so shift to the, let's just say, right mass, rest frame. I now know that if it's a two-dimensional problem, that they will shoot off at a right angle to one another, assuming that it's not a one-dimensional problem. But when you get to the end, whatever answer you get, you need to shift back. So we subtracted 2 meters per second I hat. We need to add 2 meters per second I hat at the end. All right, questions?
You mean we added 2 meters per second I had, so we have to subtract 2 meters?
No, yes, we added, thank you. So we have to subtract at the end. Sorry about that.
No, just making sure.
All right. I'm gonna shift away from momentum, let's head back to energy for a moment. I was watching Tragic Histories, there's some YouTube channel that does disasters. And one was a roller coaster disaster. And I thought, wow, that's an interesting physics problem. Now, the guy who was designing the roller coaster had basically did it by trial and error. Which seems like a rather expensive way of doing it, but they wanted to build the world's largest drop. So you go around, and then there's another hill here. Just call this H visual. What would you guess, right off the bat, is an inherent problem with this?
That it needs to go back up the drop to absorb the energy.
Go back up that.
Well, he basically needs to stop at an equal distance above the ground to where he started.
They want the thing to go all the way to the end. That's not gonna go back.
No, I mean, it's like, it needs to be like a W. Right now, it's just kind of.
Roller coasters, they generally apply brakes, so that's not the inherent issue.
Oh,
Yes?
it might be going so fast it lifts off the tracks.
And even if the cart, or the car is attached to the car can't come off, you have to worry about the people. So they made some changes, and we'll talk about that in a little bit. And then they put netting over this. And unfortunately, there was a 10-year-old who came out of his seat, hit one of the bars that was holding the netting, and was killed.
I know what you're talking about.
Pardon?
I heard about that story.
It's a very unique name of the people who are running it. Very German. Anyway,
Very
all right.
characteristic for them. The Germans, I mean.
Oh, definitely goes in the face of the stereotype. All right, so what I wanna know is, what does this height difference need to be so that you don't go flying off the track? I will give a piece of information here of, say that we know what the radius of curvature is, and we know initial height. We're basically trying to, well, actually, want to know what the difference is between these two heights so that car will not go off the track. And it is an energy problem. Actually, it's an energy and circular motion problem. So let's look at it from an energy point of view. You start out here at rest. Initial speed is 0. How much energy? What's the initial energy?
0 kinetic.
Okay.
The potential energy,
Okay.
gravitational potential energy,
Okay.
which would be, well, it would depend where 0 is.
Where do you want to make 0?
Would it make sense to do the bottom of the first drop there?
Here?
Yeah. I guess.
It's fine to use that. Remember that my heights here are based upon from the ground.
Oh, well, then probably do the ground then.
Okay. If you did it from here, we would make up a unit or make up a variable to represent that and subtract it. Eventually, it would just go away. It would cancel out. But if we did make h is equal to 0 at the bottom, I think it's a little bit simpler. All right. What's the formula for gravitational potential energy?
MGH.
Why not use the negative big G in 1 and 2 over R?
What was that?
Because we have 2 gravitational potential energy formulas. Why this one and not the other one?
Because it's an extremely small object versus an extremely large one.
Therefore,
It would be negligible to do the other way.
yeah, I guess it'll be my mind exercise. The acceleration due to gravity is going to be pretty much the same here as it is here.
Oh.
It's a small enough difference so that little g is constant, can be considered constant. All right, so we have, so my total initial kinetic energy is the mass of the car and whatever is in it, g h sub I. What's the energy at this point?
MGH, so that. Oh, is equal to EF.
Add the kinetic energy.
Yeah, it is moving. All right, so I don't know the relative difference between HI and HF. They're equal to each other, because we're going to assume that it's a perfectly, beautifully created roller coaster in that nice frictionless rails. So we have mg hi minus mg hf is equal to 1/2 mv squared. Obviously, mass can cancel out. So I have g hi minus hf is equal to 1/2 v squared. Now, I don't know what HI and HF are, I don't know, I'm trying to find that relative difference. We have speed here, I need another equation. So what's the other thing involved? The other physics concept involved in this.
Momentum.
It is involved, however, that's gonna be a more difficult way to go. Flashback to chapter 7, I think it's 7. Maybe 6.
Acceleration.
What about it?
The centripetal acceleration.
Yeah. Because we're going around a curve right here, so I do need to worry about that the centripetal force needs to be at a minimum. So if it's going really fast, just think about we got a blank, empty car shooting over this hill. If it's going really fast, unless there's something that's holding it down, the car should go flying off the tracks. In that case, if it is being held down, or somehow the car is being kept from coming off the track, what are the forces keeping it? What are the forces acting on the car at that point?
Gravity. Force due to gravity.
All right, so we got weight acting down, and
Normal force between the car and the track.
it depends on how it's being held down. The normal force would have to be acting downwards. So it's like you have wheels and you have some safeguard to keep the wheel from coming up. So the normal force is pushing down. There's some extra force acting downwards. We'll call it normal force for sure. If you are at that the trouble is